Okay, let's pick up from where we left off in the last video, which was looking at these two examples. I thought that I would start by drawing them out for you. Hopefully you've tried it on your own. Again, the more you practice this on your own, the better you're going to get at it. So I'm going to switch over to my whiteboard so that I can actually do this problem out with you. Okay, so here are two examples. The first thing that we're going to do is look up at the periodic table, and we're going to note the valence electrons that are present. And then you want to fill your orbitals in energy order. Okay, so a lot of times it's easier when you're first starting this to write out the electron configuration first. So for sulfur, our first shell is 1s. There's 2 electrons in 1s. Then we move to 2s. There's 2 electrons there. Then we move to 2p. There are 2. So far we've used up 6, 7, 8, 9, 10 electrons. So we still have 6 left. The next level that we're going to is 3s. 2 electrons can go in there. So now we're up to 12 electrons. And then we'll be into 3p, and we have 4 electrons left. Okay, so that's your electron configuration. Now what we want to do is draw a box diagram from our electron configuration. So a box diagram, you can actually physically draw boxes for them, or you can draw dashes. Either way is okay. You just want to label what you're doing. So this is our first box. This represents the 1s. Our second box represents 2s. This represents 3s. And my 3p boxes are all because I ran out of room. That's fine. Okay. And now you go through and you fill out the actual electrons, but you're doing it, you know, keeping all of your previous rules in mind. So in 1s, first you're going to have an electron with an upspin and a downspin. There's your 2 electrons. For 2s, an upspin and a downspin. Now when you're filling up your p orbital, this is the way that the electrons fill in. All ups, then all downs. Okay? With 3s, it's an up and a down, and now we get to the 3p, and we only have 4 electrons here. So first we have to fill them in singly, and then we go back and we fill in that 4th one. So we have 2 unpaired electrons for our sulfur. Now for argon, we're going to write out the electron configuration for it. You're going to notice that it's very similar to sulfur, except it has a full 3p. Okay. We'll make these boxes smaller to start, learn from our mistakes. Okay, and now I'm going to label them. It's 1s, it's 2s, it's 2p, that's 3s, that's 3p. All right, and now I will fill in my electrons. There's my 1s, there's my 2s, my 2p. Notice how it's 1s, 2, 2s, 2, 2p, 2, 4, 6, 6, okay. 3s2, and then 3p, 1, 2, 3, 4, 5, 6. So in my noble gas argon, I have no unpaired electrons. That's exactly as it should be. That is why our noble gases are so unreactive, because they have a full valence. Their outer level here completely paired up, so they don't want to have any kind of electron movement. With sulfur, you see that there's two unpaired electrons over there, so there's two spots for sulfur to accept electrons into those last two orbitals. Okay, now we've actually talked about this part before, the electron configuration of the periodic table, in terms of the blocks, right? So every group number is going to correspond to a certain number of valence electrons. So group 1 has 1 valence electron, group 7 has 7 valence electrons. As far as the main group goes, right? Again, we don't make that assumption for transition elements. And the length of each of the blocks, that's the maximum number of electrons that particular sublevel can hold. Okay, so when we say something is in the S block, well, the S block is only 2 rows long. That means that the S sublevel can only hold 2 electrons. The period number of the periodic table is going to correspond to the principal energy level of the valence electrons. All right, and I know that we've said that before, but it's good to remind ourselves of these things a few times so we can really remember it. So let's break down this picture here. Our S block elements are elements in groups 1 and 2. Notice how there are only 2 groups in the S block. That means that there are only 2 electrons that can fit in the S block, right? Or 1 orbital. Now, the next block is your P block. That's the next most common one. And if you count the group numbers or the columns that are part of the P block, you'll see that there are 1, 2, 3, 4, 5, 6 of them. And not coincidentally, your P sublevel can hold 6 electrons. So you notice in the electron configurations, it's like 1s2, 2s2, because there's 2 electron spaces, 2p6, because there are 6 electron spaces. Your D block elements are the transitions, okay? And there's 10 of those. The F blocks are the lanthanide and the actinide series, and there are 14 of those, okay? And your period number from 1 to 7, that corresponds to your N level when you're doing your quantum numbers. So here you go. Without writing an electron configuration, determine the number of valence electrons in nitrogen. All right, so how will we do that? So we can actually use, I'm gonna go back over here. So nitrogen's over here, okay? Now, we wanna know how many valence electrons nitrogen has, okay? So you can tell whether it's based on whether it's sort of in line with the element you're looking at in the same row of the periodic table or not. So any electron that's in this N equals 2 row, it's a valence electron, because like we previously defined, valence electrons are going to be the electrons that have the highest N level in your electron configuration. Well, nitrogen is in row 2. So all of your row 2 electrons are going to be valence electrons. Any electrons that came before row 2 are going to be core electrons. So how many electrons does nitrogen have that are in row 2? Well, we can start at the beginning. It has 1, 2, 3, 4, 5 electrons in row 2. That means that nitrogen has 5 core electrons, or 5 valence electrons, sorry. We can actually do this with any element on the periodic table. You know, you can go down here to selenium. So it's in period 4. That means that any electrons that are in row 4 with it are also valence electrons. So it's over here in group 6. That means that there are 6 electrons that come before selenium, 4s1 and 4s2. So 1, 2, 3, 4, 5, 6. So selenium has 6 valence electrons. So again, the location on the periodic table is what tells you what your valence electrons are and what your core electrons are. Okay. Of course, not everything works out perfectly, and there are some irregular electron configurations that we have to look at. And that happens because we have that sublevel splitting that we were talking about before, where you end up with some sublevels that have a higher N value, but they still are at a lower energy level. So like the 4s sublevel being lower in energy than the 3D sublevel is an example of that. The energy difference between them, it's not a huge energy difference, okay? It is a difference, but it's not a large energy difference. And in those cases, what happens when we're trying to fill the transition metal d orbitals that they have, we don't always end up following our sets of rules that we've already gone over, because having electron configurations that sort of don't follow the rules ends up being having lower energy levels than if we did follow the rules. And everything in terms of filling electron configurations or doing anything involving electrons and bonding, it's all about having the lowest energy level possible. So let's look at, this is your D block, okay? So if you compare it to your regular periodic table, we've taken the rectangular section out of this and we're kind of blowing it up. So you would imagine, like if you're looking at this trend here, starting with scandium, it looks very normal, right? We have 4s2, 3d1, 4s2, 3d2, 3d3, and over 3d4. Okay? But it turns out that having a full 4s sublevel and an incomplete 3d sublevel costs more energy than if the 4s, that second 4s electron, then having it jump up here and fill in that missing space. Okay, so the electron's going to do the thing that costs less energy. So instead of staying in 4s, it does leave and it fills up that empty fifth orbital in the 3D sublevel. So you end up with an electron configuration, valence configuration of 4s1 3d5 for chromium. Then it goes back to normal for a while. 4s2 3d5, 4s2 3d6, 7, 8, and then over here at copper, the same thing happens as with chromium. The electron has a choice. It can either stay in the 4s2 sublevel, or it can move up into the 3D and complete the sublevel. And it turns out that that has less of an energy cost than if the electron stayed in the 4s sublevel, so it moves. Those are your two big exceptions. And then you'll see that the trend, if you look, you could see kind of a trend to that, where you have this, like this partial filling of the 4s or the 5s in order to get more electrons into the D level that precedes it, to try to keep it at a lower energy level. So here are some of the main ones. I would like you guys to specifically focus on the chromium and the copper as your main examples that you should be able to recognize. And now we're going to start to talk about periodic properties and electron configuration. Just some of the things, or some of the reasons why our elements are behaving the way that they do. You could trace it all back to their particular electron configuration, which is directly related to where they are on the periodic table. None of that's really surprising. The main thing that we should focus on here is that it's our main points, our repeated points, I feel. The elements in the same column are going to have the same properties. And elements with the electron configuration that's closest to the noble gas configuration are going to be the most reactive ones, right? What does a noble gas configuration mean? It means that if you were to draw out an electron box diagram for it, or an orbital diagram, you would have no unpaired electrons, okay? That's what makes them so stable. They are very unreactive because everything is paired up. They don't want to gain any electrons. They don't want to lose any electrons. With your alkali metals, they only have one valence electron. That is why they tend to lose that electron. When they lose the electron, they end up with the same electron configuration as the noble gas that comes right before it. And then they form their +1 cation. Your halogens have one fewer electron than the next noble gas. That is why they try to pick up one electron from something in the surroundings. As soon as the halogens pick up one electron, now they have a valence that looks like a noble gas valence. Okay, and then we see the same pattern that we've noticed before in earlier chapters, but now we kind of see why it's happening. Okay, why does group 1 form +1 charge cations? Because when they lose one electron, they have a valence that looks more like a noble gas valence. Everyone's trying to mimic the electron configuration of noble gases in order to form stable structures. Okay, here's just a list of your unchanging predictable charges. Looks a lot like the list that we were talking about back in chapter 3 when we were looking at the naming, right? So let's look at this here. A main group element has an outer electron configuration of ns2 and p4. What charge is likely for an ion of this element? Well, remember that if you have an S2 followed by a P4, that all of your noble gases have an electron configuration that ends in P6. So this particular electron configuration is missing 2 electrons. So if it picks up 2 electrons to become ns2 and P6, ask yourself, what charge is that going to be? The charge is -2. It picks up 2 electrons, right? So now we're going to look a little closer at electron configurations of ions in general, okay? Figuring out the electron configurations of anions is not that bad, because you're just going to, kind of like we just demonstrated, you're going to add electrons onto your electron configurations. The more electrons you add to your electron configuration, the more negative your ion becomes. So sulfur went from 3s2, 3p4 to 3s2, 3p6. We added 2 electrons. The sulfur ion is S2-. Ions are a little bit different. Okay. Well, they're different once we get to the transition metals. The cations are not so bad before that. But you do have to remember that when cations are formed, the metals are going to lose electrons instead of gaining them, right? So you're going to have to remove electrons from your electron configuration in order to represent your cations. what we're going to do to write the electron configurations for cations is that we're going to first look at the charge of the ion that we want to form. So we're looking for aluminum here, and we want to write the configuration for an aluminum 3+ ion. That means that we're going to have to remove 3 electrons from the aluminum neutral electron configuration. So you're going to remove electrons from the highest energy levels first, okay? The highest energy levels, and this becomes important for transitions, the highest N values. So our highest principal energy level first. So in this case, our highest principal energy level is 3. So we're going to remove our electrons from the N equals 3 level first. And we're going to start in the highest of the N equals 3 levels, which is 3p. So we're going to remove the electron from 3p. Then we're going to move down to the 3s sublevel, and we're going to remove 2 electrons from there. All right, so we're going to rewrite the ion configuration with what remains, which is 1s2, 2s2, 2p6. And you'll notice that when we write out the electron configuration for the ion, it now has a noble gas electron configuration. Okay, so another example here. We have a magnesium atom. If we want to convert it to a magnesium cation, that's Mg2+. So we'll go to the highest principal energy level, and we'll remove electrons from there first. So we'll remove these 2 electrons from the 3s level, and we're left with 1s2, 2s2, 2p6. Again, an electron configuration that mimics a noble gas configuration. So cations, they're going to lose their valence electrons to become more stable. Anions are going to gain electrons to become more stable. Now, when you have transition elements, transition metals, you have to go through a slightly more complicated process first. You want to remove electrons still from the highest N value orbitals first, okay? Now, that is not always intuitive to people, because you did not finish by filling the highest N level orbitals. You finish by filling D orbitals. But these D electrons cannot be removed till you remove the electrons that are in. So an atom, I'm going to convert it to an iron 3+ cation. We need to remove 3 electrons from this electron configuration. So we're not going to pull them off of the 6 electrons in the 3D sublevel. First, we're going to go to the 4s principal energy level, because N equals 4 is the highest level present in the iron atom, and we're going to remove those 2 electrons. After we remove those 2 electrons, then we can remove the additional electron we need to remove from the 3D sublevel. And then we'll rewrite what's remaining: 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And that is the electron configuration of the iron 3+ cation. Okay. Another concept that we have to kind of look at is the idea of magnetism. Okay, whether something has a magnetic property or does not, right? If you have electron configurations that leave you with unpaired electrons in the orbital diagram, that means that you are going to have a net magnetic field in that atom or in that ion, all right? These substances are called paramagnetic. So paramagnetism in general means that you're going to have an atom or an ion that is going to be attracted by a magnetic field. So here, for your neutral silver, you have this 5s1 electron. there's one unpaired electron in this structure, that means that it's going to be attracted to a magnetic field, so it is paramagnetic. On the other hand, if you have something that has no unpaired, I wanted to make sure I was saying that right, no unpaired electrons, or that everything is paired up, it's not going to have any attraction to a magnetic field, okay? It's going to be slightly repelled by a magnetic field. These things are called diamagnetic, okay? So diamagnetism means that you have all electrons paired up with one another, and you have atoms or ions that will be slightly repelled by a magnetic field. And you can tell whether something is paramagnetic or diamagnetic by drawing out the orbital diagrams and looking at the actual electrons distributed throughout. Okay? So take a minute, hit the pause button, draw these two ions out, and decide whether they're diamagnetic or paramagnetic. You for real better hit the pause button. I'm about to advance forward. So first of all, we have the aluminum. We can write our shorthand for aluminum, and that is 3s2, 3p1. Okay. Now I'm going to remove 3 electrons, the 3 valence electrons from aluminum. So I'm left with the electron configuration of neon, or just the electron configuration of helium, followed by a full second principal energy level, right? Either way, when I draw out the box diagram, I see that every single orbital has a set of paired electrons in it. That means that I am looking at a diamagnetic substance. All right. For sulfur 2-, my initial electron configuration is 3s2, 3p4. I am going to add 2 electrons to that. Once I do that, I have 3s2, 3p6 in my valence. And when I draw out that orbital diagram, I again have everything paired up. This is another diamagnetic species. And notice that you can shorthand your orbital box diagrams by including that bracket with the nearest preceding noble gas before your orbital diagram, just to make it a little bit shorter for you to draw. Let's talk more about this effective nuclear charge and shielding. We started to talk about it earlier, but we're going to talk about how to calculate it now. And again, this is the actual positive charge that a particular electron is going to feel. All right, so when we're doing a effective nuclear charge calculation, we're actually going to be looking at 2 values. Z is the nuclear charge, which is going to be equal to the atomic number. Okay, the nuclear charge is the number of protons in the nucleus. That's equal to the atomic number. That's why it's labeled Z. S is going to be the number of electrons in lower energy levels, or the number of core electrons. Okay, you're going to notice that your general trend in terms of shielding is that S is less than P, or S is greater than P is greater than D. We talked about that before as to why certain things are going to screen more than others, or things are going to be shielded less than others. And it has to do with how close they are to the nucleus, okay? So I think I might have misspoke in the sentence earlier. What we're looking over here in this trend in particular is what's better at screening other electrons than other things. So because your S is a little bit closer to the nucleus, that's going to screen better than P electrons would screen because they're a little bit further away. D electrons are going to screen a little bit worse than P ones because they're a little bit further away, and so on and so on. But we can calculate an effective nuclear charge by doing some simple subtraction. We're just going to do the Z value minus the S value, okay? And what remains is the effective nuclear charge. That's the charge that the electron that you're looking at actually would feel from the nucleus. Okay, I think. Where we have this 3+ nucleus, we have the 2 core electrons that are inside of the blue mist thing that's supposed to represent the inner electrons. And then we have our valence electron outside. Okay, so to find the effective nuclear charge that this particular electron feels, we're going to take that positive charge from the nucleus, and we're going to subtract the 2 inner electrons from that charge. What we're left with is a +1 value. That is the effective nuclear charge of this particular electron. Okay, and that whole effect is called the screening effect. Okay, one thing for okay. Because screening happens by your inner electrons, your core electrons. And as we've kind of said multiple times, this is just a restatement. Your shielding means that the outer electrons are not going to feel the full positive charge of the nucleus. Subtract the inner electrons from that, the core electrons from that. Okay, take a second. And you're going to see that the valence electrons in sulfur are going to experience the greatest effective nuclear charge of the bunch.